All right, folks. All right, so we're going to take a look at 1394, number 94 again here. And I've got the picture here. It looks something like this. So this particle is moving along this path. Here's an angle theta. And r is defined by the function e to the theta in meters. And when we draw the normal force here at this point in space, or when we draw a free body at this point in space, the normal force would point something maybe like this. And you'll notice that there is some sort of angle between the normal force and, what I'm going to call the radial direction here. Now I'm going to go ahead and I'm going to put a coordinate system here, and I'm going to put it in different colors here. So let me put it in red. So right on top of this object, I'm going to put a couple of unit vectors representing the r hat direction and the theta hat direction. So the r hat direction would look something like this. Then the theta hat direction would look something like this. Now, I could put the gravitational force in here, but I think what I'm going to do is leave it off for now, because when you're talking about these dynamics problems with machinery type stuff, usually the gravitational force is actually not an important force for the free bodies. It turns out usually these internal forces are a lot larger, so I'm going to leave the gravitational force off and take a look at what these forces end up being and decide if they're going to be important or not. If I think they're going to be important, then I'll put it back in the free body. So again, notice the normal force points like this. This applied force F is parallel to the curve. And you notice that there's an angle right here, alpha, between the normal and the radial direction. This would actually be the minus r hat direction. And you'll also notice that this angle between the applied force F and the theta hat direction would also be the same angle. To see that, imagine this. Imagine this particle is moving in such a way that this alpha is going to zero, like if this particle starts backing up. And what you'll find is that these two angles will go to zero at the same time. We sometimes call those pinproofs. So before we can write the Newton's second law equations, we got to know, how to find alpha. And I did that a little bit in the latest video. Imagine that this particle moves from here to here along this path. And I'm going to draw this off to the side. So imagine it starts here and it moves a small displacement here. Let me call that ds. And there's a couple of ways we can describe this. In this picture, the ds is along here. Now imagine a displacement vector that's created by a small change in theta. This particle would move this way, and then imagine a change in r. Then it would move out. So in this picture, this ds is basically equivalent to this and this. All right, this one is a dr, this one is an r d theta. Now the reason this one's an r d theta, you have to look at this picture. If theta changes a small amount, this object actually would move this way, right? And that distance would equal r times d theta by definition of a radian. And then this interior angle here, that's the alpha that we've got to find. So the tangent of the angle alpha would equal dr over r d theta. And if we wanted to, why don't we write it like this? How about 1 over r dr d theta? And that's going to equal 1 over r. Now the r was defined by this function over here, e to the theta. And dr d theta, keeping in mind that this is our function, would also equal e to the theta. So this is equal to 1. So lo and behold, the angle that we need for our Newton's second law equations ends up being 45 degrees. In general, this is how you find that angle. You look at the vectors you're interested in, you define an angle, you look at a couple of displacements, one for the d theta and one for the dr, label the angle, go through the trig. So we've got our angle 45 degrees. Now I'm going to go ahead and write a couple of Newton's second law equations. But first I got to get rid of this stuff here. So let's see, I don't need this anymore. I'm just going to take that. I think I can just, doop, yep, there it goes. All right, get my pencil back. Oops. There we go. All right, now, for our Newton's second law equations, I'm going to go ahead and write them. So one of them is going to be sum of all forces in the radial direction equals ma in the radial direction. Now we're calling this way positive. So when we write this force equation, looking at the free body, that's going to be F sine alpha minus N cosine alpha equals ma sub r here, where that a sub r is going to be the radial component of the acceleration. We'll go ahead and find that here in a few minutes. All right? But before we do that, we got to write a second Newton's second law equation, which is going to be the sum of all forces in the theta hat direction equals ma theta hat. And for this equation, this way is what we're calling the positive theta hat direction. So the black vectors here, these are the force vectors. So that's going to be F cosine alpha. Let's see, minus N sine alpha. And then equals ma sub theta here. I think I did that right. I'm going to look at that one more time. So summing force vectors, theta hat direction. So that's going to be F cosine alpha. Then it's going to be plus N sine alpha. And that's it. So it looks good. So now what we need to do here is we need to come up with expressions for the acceleration vector. So the acceleration vector in general, remember, in radial coordinates, let's see if I can do this from memory here, looks something like this. We have r double dot minus r theta dot squared in the r hat direction plus r theta double dot, I think it's plus 2r dot theta dot in the theta hat direction. I'm pretty sure that that's right. So this term is the acceleration term we need for this, for that Newton's second law equation. And this is the acceleration term we need for this, right? So this first thing that I've underlined here, that is a sub r. And the second thing that I underlined, that is a sub theta. So we're going to have to go through and calculate these. So I'm going to go ahead and do that now. So we have r equals e to the theta. So taking a time derivative, r dot is going to equal e to the theta, theta dot. Looks like that's it. And then r double dot is going to be, okay, we got to hit this with the time derivative again. So derivative of the first term, keep in mind we have to product rule this. So that's going to be e to the theta times theta dot, right? So that's the derivative of the first term times the second. So that's going to give me two of those. Plus the derivative of the second times the first. So that's going to give me e to the theta times theta double dot. So the acceleration terms now, let's see. A sub r is going to equal, right, r double dot minus r theta dot squared. So that's going to be this minus r theta dot squared. Now keep in mind that r is e to the theta. So this term right here is e to the theta, theta dot squared. And this term right here is e to the theta, theta dot squared. So what we're going to have now is those terms are not going to survive. So what we're going to be left with is just this term right here, which is e to the theta double dot. E to the theta, theta double dot. I'm going to stop this for a minute, just double check that everything is kosher. Yeah, so I think that looks good. Right? So now the a sub r, or I'm sorry, the a sub theta, let's calculate that one. That's going to be, let's see, r theta double dot. Now in this example, theta double dot was 0. So that term is gone. And then we're just going to be left with the 2r dot theta dot. So let's see, the 2r dot theta dot is going to equal 2 times, and I'm looking now here for r dot, e to the theta, theta dot. And so that's the 2 times r dot, and then times theta dot. So that's going to be squared. So, you know, looking back at our radial term, to tell you the truth, the only thing that had survived was the e to the theta, theta double dot, but that term also is 0 because the theta double dot is 0. So our radial acceleration, 0. So the only thing we seem to need to worry about here is our theta dot acceleration. So let me get rid of this stuff and I'll write those Newton's second law equations out. So I'm going to get rid of all of this. Get my pencil back. Okay. So now, this equation now can be rewritten F sine alpha, keep in mind alpha is 45 degrees, minus n cosine alpha equals 0, because we determined that the radial component of the acceleration was 0 in this animal. Right? And then equation number 2 here, we're going to be able to rewrite this. F cosine alpha minus n sine alpha is going to equal m times a sub theta. And the a sub theta can be written 2 e sub theta, theta dot squared. Okay, so here's our Newton's second law equations. There's a pair of them, and the rest of this is to do the following. In this problem, when this thing is up here, I think it says something like 90 degrees. So at this point right here, we'd go pi over 2. Theta dot is a known value. Mass is a known value. So what we have is a pair of equations that need to be solved for f and n. So I'm going to go ahead and let you do that. I'm not going to do that right now. I'm just going to start working on another video over something else. So hope you folks have a great day, and we'll see you soon.